So we discussed before the origin of the current, why a current will be induced in the wire, and we said it must be due to the existence of an electric field, a non-conservative electric field. And this electric field, it'll point in this direction, the direction of the current, and it'll therefore make the charges move opposite the electric field, and that's how you get a current established in the wire. So we want to learn the equation that determines the relationship between the electric field and the change in magnetic flux through the loop. And that's basically Faraday's equation. Faraday's equation says if you go around this loop and you integrate the electric field dotted into elements of length that are pointing along the direction of the loop, this should equal to minus the rate of change of magnetic flux through the loop. So this is the relationship that relates the electric field to the rate of change of magnetic flux. And there's a very specific way the ds vectors that I mentioned that go around the loop are related to the dA vectors that are used to get the magnetic flux. And this is what we'll discuss in the next slide. So as I mentioned, these ds vectors and the dA vectors, they have to be related in a very specific way. If you put your fingers along the direction of the ds vectors, then the direction of the thumb will be pointing in the direction of the area vectors. So the area vector and the ds vectors have to be related this way. If you choose the ds vectors to be the opposite direction, then the area vector will be down. So they have to be related in this way for this equation to be correct. So if we have now the situation where the magnet is moving upwards, let's see how we can show that this equation tells us how to get the direction of the current induced in the loop. So if you get the magnetic flux through this loop, magnetic flux means you cut up your loop into several elements of area, many elements of area, and each element of area has a dA vector, and there's a magnetic field vector, the magnetic field due to the magnet. So and then you get the magnetic flux, the total magnetic flux, by integrating B dot dA through the whole loop, and then you're going to take the rate of change of that with time and then multiply by -1 and say that's equal to integration of E dot ds. So to get the magnetic flux, now in this particular case, the magnetic field, the angle between the magnetic field and the area vectors for all over this area, the angle is less than 90 degrees. So that means integration of B dot dA is going to be a positive quantity. So integration of B dot dA is a positive quantity. And not just that, because the magnet is moving upwards, the magnetic field is getting stronger with time as the magnet moves upwards. So that means the rate of change of this positive quantity is positive also. And so that's why the rate of change of the magnetic flux is positive. Now, if you multiply a positive number by -1, then you get a negative number. So that means that the right-hand side of this equation is negative for this particular case. What does that imply then about the electric field on this side? Well, we just showed that if you integrate the electric field dotted into the ds vectors, it's a negative number. Now the question is, does that mean that the electric field is opposite or in the same direction as the ds vectors? Obviously, to have the dot product negative, then the electric field has to be opposite the ds vectors. It can't be in the same direction. So that means that this means that the electric field vectors are going around the opposite direction of the ds vectors. And that means the electric field, for instance, here is going this way, opposite the ds vectors. And of course, that then implies that the current is going to be in the direction of the electric field, or the direction of J. And that means the charges themselves will move opposite the electric field and they'll go this way. And so that now we have a proof from Faraday's equation, or how to get the direction of the induced current. Now there's an easier way to try to get the direction of the induced current using something called Lenz's law, which we'll discuss in the next slides. But basically the idea is, imagine now this current, the induced current. This current makes its own magnetic field. What direction would the magnetic field due to this induced current only be? the magnetic field due to the induced current will be as shown in red. And you can try to go back to the previous chapter to remember how we found the direction of the magnetic field, knowing the direction of the current. So this means that it's as if the induced magnetic field is trying to prevent the magnetic flux of the original magnetic field from increasing. Because as you move the magnet upwards, the magnetic flux through the loop is getting bigger. So it's as if the induced current wants to make a magnetic field to prevent the magnetic flux from increasing. And this is the fundamental idea behind Lenz's law, which we'll discuss in the next file.